Alright, so we're going through the multiple choice. We have calculated a 95% confidence interval and prefer for our next confidence interval to have a smaller margin of error without losing any confidence. In order to do this, we can, number one, change the z-star to a smaller number. Now, the z-star is the level of confidence. So if we change the z-star, we change the level of confidence. So 1 is out. 2, take a larger sample. Now, the margin of error equals z-star times the standard error. So the smaller the standard of error, as the standard error gets smaller, the margin of error gets smaller. Smaller the standard error, smaller the margin of error, assuming that the z-star stays the same. If the z-star stays the same, then the only way to make the margin of error smaller is to make the standard error smaller. Well, how do you make the standard error smaller? Standard error equals the square root of p hat times q hat over n. N is the denominator of the standard error. So the bigger that standard error, as n approaches positive infinity, that is, as it gets bigger, okay, the the standard error approaches 0. So, or it gets smaller. Okay, so as n gets bigger, the standard error is going to get smaller. It's an inverse relationship. The bigger that n is, the smaller that the standard error is. So to make the margin of error smaller, we want to make the standard error smaller, so we make the sample size bigger. Okay, now if we take a smaller sample, it'll make the standard error bigger as n approaches 0, the standard error approaches positive infinity. That is, as n gets smaller, then the standard error is going to get bigger. All right, so the only right answer for this is 2 only, which is B. So that's number 1. 2 is B. 2 only. Now, number 2. Which is true about a 95% confidence interval for a population proportion based on a given sample? We are 98% confident that other sample proportions will be in our interval. All right, now look, there are 2 basic interpretations, 2 statements we make about a confidence interval. One is the interpretation of the CI, and 2 is the interpretation of the level of confidence, which is really a statement about how confident we are. Okay, so the interpretation of the CI, okay, sorry about the sloppy writing there. The interpretation of the CI, it always has the same form. We are, and then it's whatever percent, blank percent confident that P, whatever P is, whatever P represents, is between the CI numbers. Okay? All right. So there's nothing in this interpretation of the confidence interval that says anything about other samples. All we're saying is we have a 95% or some percentage of confidence that P, the population parameters between these 2 numbers. We are not We are making no claim about any other samples. Why not? Because of sampling variability. It could be that this sample is 20 sigmas away from the true P because of some weird, statistical fluke. And that no other sample will ever occur in here. Okay, we don't know that. All right, we're simply making a statement about P, and no statements about confidence intervals make any statements about other samples. Okay, about other sample statistics, other p-hats or other y-bars. Okay, that's statement number one. Now, in terms of interpreting the level of confidence, okay, the level of confidence, 95% or whatever of similar samples, same size, random independent, not too big, not too small, yield a CI that contains P, whatever P represents. Okay, and you always have to put that in, okay? Is there any mention about other samples? Absolutely not. Okay? There are no other samples. Both interpretations, the interpretation of the confidence interval and the interpretation of the level of confidence, make no statement about other samples. They only make statements about P, the population parameter. So one is absolutely, totally, completely, and positively out. Two, there's a 98% chance that our interval contains population proportion. No. The confidence interval is a statement of confidence. There's nothing about probability. We're not saying there's a probability about where P is. P is either in the interval or it's not. There's a 100% probability it's either in or not. It's disjoint. It's not like partially or whatever. Okay? All you ever say is confidence. Do not ever say there's a chance. That implies that P is moving around. So, 2 is out. 3, what is true? The interval is wider than a 98% confidence would be. Well, of course it is, because Z star is bigger. The Z star for 98 is what, 2.365 or something like that. And the Z star for 95 is 1.96. So, CI equals Z star times the standard error. So this number is bigger than that, so it has to have a bigger CI. It has to, if it has the same standard error. All right, so the only possible answer is 3. Okay, so 2 is D. 3. Okay, we have calculated confidence interval based on sample size n equals 100. Now we get a better estimate with the margin of error is only 1/4 as large. Okay, you want to cut this, you got a margin of error equals some Z star times the standard error. Okay, you want to reduce it by some number. We'll call that n. Okay, then, no, let's not call it n because that's the sample size. Let's call it x. You want to cut it by some number x. All right, you want to cut it in half. You want to cut it into a third. You want to cut it to a fourth. Okay, then the new sample size, we'll call this n prime, the new sample size, must equal x squared times the old sample size. We'll call this n sub new, and this is n sub old. So if you want to cut it in half, you got to take the old sample size and multiply it by 4. If you want to cut it by a third, you got to take the old sample size and multiply it by 9. You want to cut it by a fourth, you got to take the old sample size and multiply it by 16. So how big is your sample size? It's got to be 1600. So the answer is E. Don't forget that little rule of thumb. Whatever number you want to reduce the sample size by, 2, 3, 4, 5, whatever, square it and multiply your old sample size by that. That's how big your new sample size has got to be. If you wanted to cut it in half, you'd need 400. If you wanted to cut it by a third, you'd need 900, and so on. Okay? So, 3 is E. Let's make a new page for 4. Certain populations bimodal rate its mean, so we'll collect a sample, which should be true for the large. Okay, we got a large sample from a bimodal population. Okay, here we got heights of men and women. And I keep using the same stupid example, but anyway. We wouldn't normally put them together. Right here they are. Bimodal. Okay, we got a mean for the men, mean for the women. Then we have a mean for the whole population. It's somewhere in here probably. Okay, an average height for the men and women taken together. Now, if we take a really big sample, let's say a couple of hundred people, so let's say this is how many people live in the United States? 300 million, or I don't remember anymore. So here's our 300 million people in the United States. Okay, let's say it's adults. Let's say it's 200 million adults, whatever. Okay, we take a couple hundred people as a sample. So we have a tiny little sample, just a few hundred people. This is like the scale's way off. Okay, that little sample would have a shape approximately the same as the population. If it's big enough, the distribution of the sample itself is going to look like the population. Now, if you take another sample, it's going to be maybe shaped a little bit differently. But if the samples are big enough, they're probably all going to be bimodal. They all have slightly different distributions and different means, but they will probably be bimodal. Okay? So, for 4, the distribution of our sample data of itself will be bimodal. That's true. Okay. 2, if the sample size is big enough, regardless of the shape of the population, if it's big enough, the sampling distribution of the sample mean will be approximately normal. That's true. That's a central limit theorem. Okay, if the sample is big enough, it will distribute by mean sigma over the square root of n. It'll be approximately normal sampling distribution. If n, let's say if n is just bigger than 50, this is going to be the case. Okay? No matter what the population looks like, no matter how screwed up it is. Okay? All right, so 2 is true. 3, the variability of the sample means will be smaller. Okay, a large sample over a small one is going to have, the bigger the sample is, you're going to have a smaller standard deviation, right? As the standard deviation gets smaller, because n gets bigger. So the variability is a function of the standard deviation. It's the square root of the variance, remember? So it's going to, bigger the sample size, the smaller the variance, the smaller the variability. Okay? All 3 are true, 1, 2, and 3. So 4 is E. 5. Yeah, let's scroll up on 5 here. 5. We got to go to the next page in a second. Okay, manager expects 70% of the oranges to exceed the weight requirement for grade A designation. How many apples must he sample to be 90% confident in estimating the true proportion to be plus or minus 4%? Okay, so he wants the margin of error. This plus or minus business, that's the margin of error. He wants the margin of error to equal 0.04. So the margin of error equals Z star times the standard error. Okay, so 0.04 equals, now what does he want? He wants 90%, 1.645 times the standard error. Now, we're told the population parameter, okay? That is P equals 0.7. That's the percentage of oranges that exceed the weight requirement. I guess you got to be 0.7 or greater to be grade A, right? So Q equals 0.3. So it'll be 0.7 times 0.3. Now what we have to do is find n. We don't know what n is. We have to find the sample size. Okay, so we're going to have to do some reciprocal operations here. Okay, we've done them in other problems. The first thing I'm going to do, I'm going to take 0.04 and divide it by 1.645. I'm going to divide both sides here. I'm going to divide both sides by 1.645 equals 1.645 over 1.645 times the square root of 0.7 times 0.3 over n. So in other words, it's all multiplication, so I can do this reciprocal operation to get rid of the coefficient of the radical. So now I've got 0.04 over 1.645 equals the square root of 0.7 times 0.3 over n. Now, maybe the easiest thing to do here, there's a couple different ways to do this. Let's square both sides and get rid of this radical. So I have 0.04 over 1.645 squared equals 0.7 times 0.3 over n. Now 0.7 times 0.3 is going to be 0.21. Now we can do a means extremes. We can multiply both sides by n and divide both sides by 0.04 over 1.645 squared. So n is going to equal 0.21 over 0.04 divided by 1.645 squared. That's correct. Okay, now I just want to take a look at this. All right, this isn't how I did it the first time. Let's put it in the calculator and see if I get the right answer. So I'm going to drag this over here. So I'm going to clear. So we're going to take 0.21, 0.7 times 0.3. Yeah, that should be. I just want to be sure about this. 0.7 times. I can never do this in my head. I always get this wrong. Yeah, it's 0.21. Okay. Divided by, open parenthesis, 0.04 divided by 1.645 close parenthesis squared. Okay, that's the right answer. And so we're always got to round up. So it's approximately equal to, well, it is exactly equal to 356. The sample, you got to do 356 oranges to have this confidence interval of 0.04. All right, number 6. So number 6, a p-value indicates the probability that the null hypothesis is true. No, the p-value is not about the null hypothesis. It's about the alternative hypothesis. Okay, it indicates the probability the alternative hypothesis is true. No. What's wrong with both of these statements? True. True. Okay? True. It's a filthy, dirty word. We never use it. Okay? C, the probability the null is true. No. True. You see the word true? It's wrong. True. It's bad. All right? D, the probability of the observed statistic given that the null hypothesis is true. That's it. Okay? All right? We don't prove anything. All right? But we do assume that the null hypothesis is true. That's the only time that true is allowed to be used. Okay? Or maybe there's other instances. I don't know what they are. But we don't prove anything is true. We never do that. We never prove anything is true. Never. Okay? A p-value indicates E, the probability of the observed statistic given that the alternative hypothesis. No. It's all about everything is in terms of the null. Okay? Why? We're not attacking the alternative hypothesis. We're attacking the null hypothesis. Okay, we accomplished nothing if we somehow fail to prove the alternative hypothesis. It's the null hypothesis that we are interested in overthrowing. So the only right answer is D. Now I got to get to the other page here. Give me a second. No, that's not what I wanted. What the heck is the other page? Here, page 2. There we go. So where is it? There it is, sideways. That's nice. All right, let me get this thing set up here. I should have had this done earlier. Sorry to keep you waiting. All right. And let's make it a little bigger, 75. Okay. All right, statistics professor wants to see more than 80% enjoyed taking the class. At the end of the term, she takes a random sample and asks an anonymous survey if students enjoyed taking the class. Which set of hypotheses she used? Okay, A is no good because the null hypothesis has a less than sign in it. Ditto for H is wrong. I'm sorry, C is wrong and D is wrong. Now, B and E both have the null hypothesis where P equals 0.8. So either of those on that basis could be right. So let's look at the alternative hypothesis. Well, she wants to see if more than, so the alternative hypothesis is P is greater than 0.80, so B is right. So 7 is B. That wasn't too bad. That was quick. 8. Not wanting to risk poor sales for a new soda flavor. A company decides to run one more taste test for potential customers, this time requiring a higher approval rating than they had for earlier tests. The higher standard of proof will increase what? Okay, well, what are they trying to avoid? When you increase standards of proof, increased standards of proof decrease type 1 errors. In other words, it makes it harder to reject the null hypothesis. Okay? So, I'd set alpha, instead of having alpha be 0.05, I make alpha equal 0.0001. Okay? I've made it, so in other words, the sample statistic, the p-value, has to be really improbable before I allow it to overturn the null hypothesis. What's another way of looking at this? You're putting somebody on trial. You're trying to avoid convicting an innocent man. Convicting an innocent man is a type 1 error because the null hypothesis is that he's innocent. Okay? Nothing, you're skeptical. He didn't do anything. Okay? So, increasing the level, it would mean not just he signed a confession, not just you have an eyewitness, but you have to have the gun, you have to have the body, you have to have DNA. So you just keep adding more and more things where you're going to, so you're really trying to avoid convicting an innocent person. And so you're certainly making it impossible, almost impossible that could happen by increasing the demands of evidence. All right, so you're lowering the risk of making a type 1 error. Okay, but what's going to happen? Guilty people are going to get away, and that's a type 2 error. So in other words, increased standards of proof decrease, but increase type 2 errors. Okay? All right, so innocent people are not going to prison. That's good. But criminals are also not going to prison, and that's bad. And criminals, guilty people being let off, being found innocent, is a type 2 error. So if you increase standards of proof, we're not saying that's bad, you will decrease type 1 errors, but you will automatically increase type 2 errors. And there's always this tension between type 1s and type 2s. All right. So what were they trying to do? What they were trying to do in context was avoid deciding that a new soda was really preferred. Okay? They didn't want to go through the expense and the waste of putting out a new soda that people really didn't like. Now, what was the danger? That they actually had a soda that people actually did like better. In other words, rejecting the null hypothesis that it's really not better than the old soda. And then lost the opportunity to increase their sales and maybe save their company or something. So, all right, type 1s, type 2s. 9. A manufacturer is testing one of his machines to make sure the machine is producing more than 90%. So, let's think about this. The null hypothesis, H sub 0, P equals 0.97. H sub A, P is greater than 0.97. Okay? You're hoping that it's producing better than 0.97. Okay, now you get a p-value of 0.122. The p-value. P is large. Null takes charge. You fail to reject the null. Okay? Oh, and what happens? Unknown to the manufacturer, see here, the angel Gabriel appears to you in a dream and tells you the machine is actually producing 99%. I mean, that's the only way you're ever going to find out. It's actually producing 99% good parts. Okay? So, it's actually producing, so what are you going to do? You're going to fail reject the null. You make a type 2 error. Okay? You fail to reject the null, making a type 2 error. Alright? Because you should have rejected, because the machine is better. In reality, the machine was better than 0.97. In reality, it is 0.999. A type 2 error can only happen if the null hypothesis is false. A type 2 error can only happen if H sub 0 is false. A type 1 can only happen if H sub 0 is true. I realize this is self-evident, but it's a good thing to think about. It'll help you make sense of this stuff. Okay, so you're not tearing your hair out. All right, 10. Which is the following is true about type 1 and type 2 errors? Type 1 errors are always worse. No. No, they're not. Okay? Yeah, type 1s are worse if you're sentencing somebody to death and they didn't do it. That's bad. But type 2s are worse if you reject a drug that could help cure cancer or keep somebody alive longer when they got cancer. You reject it, but it really does. That's really bad, I mean, if the drug doesn't do any good, so what? The guy's got cancer, it's not going to hurt him, but it could help him. So type 2s can be bad also on the individual level, and these both can be bad on the social level, on a larger level as well. Okay, so 1 is wrong. 2, the severity of type 1 and type 2 errors depend on the situation. Well, I just explained to you how that's the case. 2 is right. I just gave you 2 different situations, one in which a type 1 is worse, one in which a type 2 is worse. Okay, so 2 is true. 3, in any given situation, the higher the risk of type 1, the lower the risk of type 2. That is true. Okay, so 2 and 3 are true. So E, 10 is E. All right. So that's about it. Any questions, send me an email.